Yeah. So good morning, everybody. So I think last time we have done matrices. So I'll take a very simple problem and then we'll go to finding the moment of inertia and the principal axis problem. So let me revise it through an equation solver. Suppose we have three equations. Okay. So
you have to share this.
I think you can see this. Right? You can see the screen now?
Yes. That's good.
What I'll do is instead. So if we have three equations, let us say a1x, b1y, c1z, a2x, b2y, and c2z, and so on. Okay, so the right hand side is this. So we can write this simultaneous equations as a matrix of all the coefficients and a column matrix, so that when you multiply you get the left hand side and you have the right hand side. So these are our three equations. Okay, so we'll use the matrix formulation which we did last time to solve this and find the values of x, y, and z. So suppose I have the coefficients a1 as 1, okay, b1 as 2, and c1 as -1. So these are all the coefficients. Okay, and these are your unknowns basically, x, y, and z, and this is your right hand side. Okay, so let us put so there would be different ways of solving it, right? So I have done it by this thing. One thing is you can find the inverse for this. Okay, so here you can see that this array which I have selected. So what you will do is you'll say equal to M inverse. I think I told you how we named this matrix last time. So that is, we have given the matrix name as CF. Okay, so I select CF and Control Shift Enter. So this is give us the inverse of this. Okay, then how do we calculate the x, y, and z? Is that you will have to multiply the inverse. So this will become an identity matrix. If you multiply this CF minus CF, this will become an identity matrix. So therefore on the left hand side you will have x, y, and z, and you will have to multiply the inverse with the right hand side. Okay, so here what we have done is this. Okay, so we have multiplied the matrix. Okay, so that is B6 to D8. So that is this matrix. So multiplied with this. So this will give us the values of x, y, and z. Suppose you don't want to do that. Okay, so you can write it in a single line. Okay, you have to multiply the matrix, obviously. Okay, so the inverse of this multiplied by this value will give us the values of x, y, and z. Okay, so let's come to another physics problem where we will use some of these properties which we have learned. Okay, so what is the principal axis or principal axis of inertia? So it is an axis around which, okay, the product of the inertia is 0. Okay, so we have already done this in your 12th standard. We have found for symmetric bodies the moment of inertia around the center of mass, and then we have used the parallax theorem, the perpendicular axis theorem, right? So for symmetric bodies, it may be obvious that the principal axis, which are the principal axis, but irregular shaped bodies, their coordinate system may be difficult to determine this intersection. So we will have a general method, okay, a general way of finding this principal axis and the moment of inertias and the directions. So let us start with what we
Tiger,
know. Yeah.
Tiger, can you enlarge a bit your
Yeah.
page size?
You can increase
Little
the
more.
view. Increase the view.
I mean, because font size is already 16.
Yeah, thank you.
Okay. So L is that's angular momentum is nothing but r cross p. For n number of particles, you can sum it over I, as I goes from 1 to n, right? And p is nothing but m into v. So m being a scalar, so you can write it as mi ri, and v as omega cross r. Okay, so we use this expansion E cross B, and we can write this result, which will result into mi ri square omega minus mi ri dot omega into ri. I hope so this is clear. Okay. So why I would need this is for writing the moment of inertia tensor. Okay. So we have this, but what is omega? Omega, we are dealing in Cartesian coordinate system, so it will be omega xi, omega yj plus omega zk, and then ri as xi, yi, and zk. So let's substitute that into this. Okay, so if you substitute that into this, yeah, so let us go component wise. So let's just take only the x component of it. Okay, so if you take the x component of it, so this is like mi ri, just take omega x, okay, and omega is substituted here as omega x xi, y, and so on, right? And ri is taken as xi. Okay, now here if you expand this, so what you will get here is ri square minus xi square, but this will result into this is going to what? Xi square plus yi square plus zi square. So this component will be your yi square plus zi square. Okay, omega x, and then minus, we can just, so finally what I get, the Lx component. Okay, the momentum, that would be, we can write this as Ixx omega x, Ixy omega y, Iz omega z. Okay, so the minus sign is absorbed into this. Okay, so finally what is Lx? So,
Shekhar,
yeah.
previous page, the
Hmm.
last term should have been
Sorry,
yi
so this is
xi yi.
Zi. Sorry, this should be Zi. Yeah.
No, I think with omega y it should
YIXI.
be xi
No, this
zi.
Zi. That's what I'm saying. This should be Zi. Yeah. So MIXI Zi. Yeah.
No, Shekhar, with omega y it should be xi zi, and omega z it should be xi yi. The typographic.
For omega y, y term will not come. Omega z, z term will not come in the product.
In the product.
No,
No.
it should.
It should. I just see.
In the final expression, it will change.
My symmetry requires that with when you
Yes.
take ixy, it will not have z in it.
No, okay. That's, anyway, it's,
Yeah. This is
yeah, corrected. Yeah, that's what I'm saying. It will be xi zi, omega z, xi yi, omega y. So this error is here. Yeah, this error is, that's what I'm saying. It should be a zi.
Yeah, the last.
Yeah, so this term is zi. I agree to it. So this is Lx. Okay, so where your this term, which we'll call it as Ixx, the x component of the moment of inertia, that is summation mj, okay, yj zj square. So you will generalize it, and then these are the principal moments, these are the product moments, okay. And similarly you can see here that Ixy is equal to your yx, okay, because you will get the symmetric terms, so it will give you the same result. So why I'm saying is this is because Ixx, Ixy, Ixz, so this, so your Lx, so this is, now the left hand side also I write it in a matrix form, L as Lx, Ly, Lz. So basically you're constructing three equations. So Ixx, that is this term, okay, Ixy, which is this term, okay, Ixz, which is this term. So you'll multiply with omega x, omega y, omega z, we will get this. So similarly for Ly and similarly for Lz. Okay, so we have the angular momentum, okay, in terms of components Lx, Ly, Lz, and we have put it into a matrix form.
I think at this point, it will be useful, especially for there are students from first year, second year also, to explain what is happening here, what are we doing here. Okay, that what is tensor, and how angular momentum and angular velocity need not be parallel.
Yeah, I'm coming to that.
Yeah, thank you.
Okay. Yeah. So basically now we have constructed this. Okay. So now this L, so now this is what we call as moment of inertia tensor. It's a vector, and then omega. So it is not necessary that this product I omega will be necessary in the direction of L. Okay. So we will have to find direction such that this L and omega are in the same direction. Okay, so that's the problem. So we have built the problem. Okay, So now with the components here, so these are all the three components. Okay. So the diagonal elements are called the moment of inertia, and the x and y components are product of inertia. Okay. So the implication of the above equation is that in many situations of importance, right? Even for bodies of symmetry, the angular momentum L, which I was just saying, okay, and the angular velocity vector are not parallel. Okay. So even in symmetric problem, so our job is to make them symmetric. So if you get it symmetric, then your angular momentum vector, okay, will be in the direction of omega. Then this tensor, which is your moment of inertia, okay, can be represented as a scalar function. Okay. So this introduces considerable complexity in the analysis dynamics of rotating bodies in 3 dimensions. Now, to search for the principal axis and moment of inertia as an eigenvalue problem. So till now, we have learned that L is equal to I omega. So this I is a tensor, which is a 3 by 3 matrix, and we saw how to calculate the components. Okay. So if I am able to represent, do this, is that this I and omega, if I am able to write it as lambda times omega, okay, so that means in this case, then L will be in the direction of omega, and your lambda, which is a scalar, so it's a scalar multiplied with a vector, so it will be pointing in the direction of omega, and L also will be in the same direction as omega. Now to how to achieve this, so in mathematics, so we have, let's say, any vector operating on a function or a vector here in this case, okay, gives you some value, which is a scalar, and the function back. So the function here is the omega here. Okay, so this kind of problems, so the function has to be returned. So this kind of problems are called as eigenvalue problems. Okay, and these values, which are the scalars, are eigenvalues. So here in classical, in quantum mechanics, you will have psi, and that will, you will not get any information from this. What are calculated are only the eigenvalues in quantum mechanics. Okay. So, but here we will need to find the eigen vectors, which will give us the direction here. Okay. So, so this is basically a problem. So L is equal to I omega. So I components we have found, okay, from here. Okay. So these are all the I components. Okay, and how to calculate those components that we have seen here. So this is what we will be requiring to create this create this moment of inertia tensor. Okay. So how, once you build the tensor, okay. So this is our problem is now if we can write it like this, okay, where lambda will be your eigen values. Okay, so I can rearrange this, okay, I omega as is equal to lambda omega if I take it on this side. Now when I take it on this side, this is a 3 by 3 matrix, lambda is a scalar, okay, but if I multiply it with 1, okay, in matrix 1 is nothing but your identity matrix, okay, so that so it's a diagonal matrix here. So if you solve it, you will get 1. So you're not changing the problem anyway, okay, except for you're multiplying it with 1. And the right hand side will become 0. So if we solve this, like here it is 1 1, but it is xx as with the previous notation minus lambda. So only lambda will be in the diagonal elements. The rest of the elements remain unchanged. Okay, so we'll have omega 1, omega 2, omega 3 is equal to 0. So once we have built this, so the next is the necessary condition for a set of equations to have a non-trivial solution. This we know from mathematics. This, if you take the determinant of this, okay, that is I minus lambda 1, this should be equal to 0. So what we'll do is basically solve this determinant to get lambda. Okay, because we have calculated what are the i's, all these I components. Okay, what is left out is lambda. So we'll get those lambdas by taking the determinant. So once we take, we know I minus lambda 1, find this new matrix. Now this determinant will give you a non-trivial solution for lambda. Okay, so the above formula, so if it's an n degree polynomial, then lambda will have n roots. Okay, so if it is 3, then it will have 3 roots, and so. So I hope I'm clear till here. Okay, we'll, as and when required, we'll have to look back, but so once we find the determinant, we get the lambdas. Okay, so the principal axes are the eigenvectors of this tensor. Now here you see this when I did this. Okay, so when you diagonalize this, when lambda, okay, lambda 1, okay, so what has happened? L is parallel to omega. Okay, so lambda 1 will not give you any direction as such. In that case, your lambda is in the direction of omega, and what was the other condition is that you diagonalize the matrix. Okay, so you diagonalize it. So this one is diagonalized here, so it will have only the diagonal components, and that will be your principal axis. Okay, so the principal axes are the eigenvectors of the tensor I. Okay, and the principal moments are the eigenvalues. Okay, so you have got the eigenvalues from finding the determinant. Okay, and then we will find the eigenvectors. Okay, so how do we find the eigenvectors? Is suppose you have a 3 by 3 matrix, we will get say 3 lambda 1, lambda 2, lambda 3 as a solution. Okay, so we will take, let's say, lambda 1 first. Okay, substitute it back into that equation, and then find the eigenvalues for it. Okay, so
Shekhar,
yeah,
with your permission, can I speak something?
yeah, sure.
This is for information of all the students. These eigenvalue equations are not necessarily only in case of matrix. They are also there. For example, if I take e raised to lambda x, then it's an eigen function for operator d by dx. So if I operate by derivative operator d by dx on e raised to lambda x, it gives me lambda times e raised to lambda x back. Right. So there lambda is called eigenvalue, e raised to lambda x is called eigen function of d by dx. The word eigen means proper. So when you say eigenvalue equation, it's a proper value equation. Eigen function is a proper function. Eigenvalue is a proper value. So I mean, this is basically probably German word, eigen. So we don't understand in the right perspective because we don't know the meaning of this word. And the moment of inertia tensor, which Shekhar has just shown you, it does not have give you angular velocity I mean angular momentum parallel to angular velocity, if your choice of axis, moment of inertia definitely depends on choice of your axis. So when you are actually diagonalizing it to make sure that you find directions such that your angular momentum is parallel to angular velocity, essentially what you are doing when you find lambda 1, lambda 2, lambda 3, three eigenvalues are moment of inertia values along those three directions. So if you take those three direction as your axis, then your moment of inertia will be a diagonal matrix, and I omega will become actually parallel to omega. This is what we are trying to say. This is very important in mechanics because there are issues like uh, even when you don't if you leave a body to rotate itself, for example in car, okay, the wheel, if it's not properly aligned, then it will require a torque to continue it rotating even if in absence of friction. So you need to align it properly so that you don't need torque. Okay, these are the problems with rotational motion equations, and there this moment of inertia tensor diagonalization to find out the right direction is important. This is theoretically. Okay, practically you go to your car workshop, they have a better way of aligning wheels. Sorry to interrupt, Shekhar.
Yeah.
I'm
Uh,
done.
so that's what is the job. How to get this alignment is okay. So L in the direction of omega is that. So we will look at this equation where this condition is satisfied. Then uh, L will become parallel to omega, and as Modi sir said, we will not require any additional torque, so it will be a free wheel. So basically point is finding out this axis, okay, and this values, from this values you will get the axis. Okay, so let us take this problem. Yeah, so oh, this problem is given by Mahesh. Yeah, so consider a rectangular massless frame with massive identical particles. Okay, so you have basically, let's say a square, okay, and you have masses, well, let's say 1, 2, 3, and 4 at the four edges, okay, and the axis is passing through one of these masses. Okay, so that's the problem we have here. So four masses, but the axis is passing through one of the masses. Okay, so since it is passing through one of the axes, okay,
and perpendicular to the plane.
Yeah, and perpendicular to the plane. So then the length is like 3 units, and the breadth is let's say, okay, 2. Okay, let's say 3. Okay, so the length is 3, the breadth is 2. Okay, so since the axis is passing through the, let's say, mass, let us call it m0, then the coordinates of that will be 0, 0, 0. This coordinates will be, let's say, uh, if you take this as your x-axis, then this will be 3, 0, 0. This will be 0, 2, 0, and this will be 3, 2, 0. So I can write it down. Oh, okay, maybe. So let's say this is 0, 0, 0. Okay.
You can make it text, and then that way.
I'll put a comma. So the other one is 0, 3,
300, right? x coordinate is 3.
And this will be, oh sorry, this is
300, yeah.
30. So this will be 0, 2, 0, and this will be 3, 3, 0. Okay, so let me start with this. Okay, so let me take this as the first mass. Let me say the mass is m1. Okay, and this coordinates are 300. Okay, for the first mass. Okay, on the x-axis the coordinates are 300. For the second mass, let's say this one. Okay, the mass, let us also take it as m2 as 1, 0, 2, 0. And for the third mass, okay, and let the mass be 1 again, and we have the coordinates 3 to 0. Okay, so this is a problem. So the first part of the problem, as we discussed, is to build this tensor. Okay, so moment of inertia tensor. So if you remember this component is your Ixx, Iyy, and Izz. Okay, this, if you just recollect what was the formula, it was I mass yi square zi square. So if it is xx, okay, so we'll have to take m1. Okay, so this will be y1 z1. Okay, then we'll have plus m2 y2 square plus z2 square plus m3 y3 square plus z3 square. Okay, so what I can do is I'll just construct here 1, so the remaining can be done. Okay, so you'll have to enter this into each cell specifically. So what was the formula for us? It was equal to m1. Okay, so when you're taking m1 for this element, it is y1 square plus z1 square, right? So you will have y1 square plus your z1 square there's a multiplication sign missing here, plus, okay, so you'll take your m2, your y2 square plus your z2 square, again a multiplication sign here, plus we have m3 square plus you have your z. Hope everything is right. So this is how you calculate, okay, this element. Okay, so the next element will be what? So when you're doing this element, it will be m1, okay, into x1 and y1 plus your m2 into x2 into y2 plus m3 into y3 yeah. So when we did this, you remember this. So your ixy is minus, okay, of summation of all this. So that's why you put this minus sign here. So that's how you can calculate this moment of inertia tensor. Okay, so the elements work out to be 8 minus 6. You can see that this also works out. This is ixy and this is iyx. Okay, and they're equal. So from this equation also you can. So ixy will be equal to iyx. Okay, so this is one part of solving this. Okay, now so next time you have, let's say, only two masses, then you will need only m1 m2 and the coordinates of that. So if you have four masses, then as we have in this case, but if it is passing through, let's say, center, then you will have to take four masses. So if it's a cube, then you can have 8 masses and so on. So so once you have built this, so your moment of inertia tensor is calculated easily. Otherwise you will have to put in a lot of efforts in calculating this, but once you have programmed it, you just have to change the values and you will get the moment of inertia tensor. Okay, till here any problems? I can go to the next step. So we have constructed this. Okay. So yeah.
Is there any shortcut to building a tensor, or else we have to do it like tediously, like every formula?
But you have to do it only once. Then you have to just enter those values. So next time you don't have to do it. You have to just build a template once. That's
Okay,
it.
sir.
Because each cell has a different formula to be fed in, right?
Yes, sir.
So we'll have to do that individually. But once it is done, now this is our tensor for us. So this is the matrix tensor. Okay. So that's why I said it is always better to create a template. So fine with this? No
Yes,
problem
yes.
with this calculation part of it? Okay, now let's go on to find a diagonal matrix. We have to diagonalize it. Okay, so when this is diagonalized, whatever values, for what values of it, it will get diagonalized means you see here. So this is lambda 1. So this is what we have to find, this lambda, such that we get this matrix which will be the lambda 1 as a diagonal matrix. So we have to find these values here. So for that, what we said is, if you have to find lambda in this situation, then so the determinant of I minus lambda 1 should be equal to 0. Okay. Now in case of Excel, what we'll have to do? Okay, so what we'll do here is we will take three values of lambda, let us say. Okay, since we'll get three equations here. So randomly, this colored one is some values you can put here, like say, oh, how to put those values, we will see. Okay, means how to choose proper values. Okay, so now when I do this, now let's come here. Now the right hand side is 0 right here, if you look. Okay, so for this element, okay, so this is element is what? We'll find the determinant, as we have said that. Okay, so the determinant of what? I. Okay, so I is your S now here, what we have named. Is this clear? So that I which was there, okay, is S, okay, minus B. Now what is B is an identity matrix. I have defined it in sheet 1, so I can keep taking that, say I here. Okay, so that is okay. So B is an identity matrix. I didn't put it here because it is already defined, and you can't in Excel give the same name set in different pages. It will go take that value in if you have defined that array in any of the sheets. Okay, into, so this is lambda I, right? So lambda, we are saying let it be 3 for the time being. Okay, so this determinant should be equal to 0. Is this clear? We are creating this situation here. I minus lambda 1, this should be equal to 0. So what I have done there is determinant. So I is your S minus, okay, lambda, we have chosen some random value. Okay, so into 1, that is, so lambda S minus this cell and into the identity matrix, which is B in that case. Okay, so the determinant is set to 0. So but we don't know the proper values of lambda till now, where it will get diagonalized. Okay, so similarly, this is I can write here if you want like this. Yes, saying that omega x, omega y, omega z, which I have written here. So similarly, you can calculate the next element. That will be determinant of S minus B, the second lambda value, okay, which we are expecting. Okay, and since I'm expecting 3 lambda values, so I say into 3. Okay, so is this clear? Any doubt with this part of setting up this determinant? So S minus lambda, which you're taken as randomly, into the identity matrix. So this determinant is to be set to 0, but we have written here, but we have not still set it to 0. Okay, how to do this is that this has to be set to 0. That means this values, now 897 has to be set to 0. Okay. Any issue here? No. Okay, so now we can go to data. Okay, so there you will find data analysis and solver. Okay, so go to solver. Okay. Here, this is useful when you have only one or two equations. In set objective, you set any random cell. Okay, you put just some random value and say maximize. So this has got nothing to do with the problem as far as we are concerned. Okay, so you can use this if you have a single or value problems, then it becomes easy. So you can set the value to 0. But since we have three equations, we will. So what you do is set objective some random cell, you can set it. Okay, sometimes it will say it should be a function, then just say put equal to some value 1 to whatever it is and maximum. So this part of it is not anywhere concerned in the problem. Okay, now the actual problem part solving comes here. Okay, so what is that we have to change? So by changing variable cells, so what is that we have to change is that we are interested in changing this cells which we have taken as random. Okay, fine. And let me just delete this part. Now let's add a constraint. Okay, so what is the constraint? These values which are calculated, which are determinant minus lambda I. So these are your cell references. This should be equal to, in our case, the constraints. What are the constraints? That the right hand side is 0. Okay, and then you just say okay. Okay, so sometimes you can unclick this also, no problem. Constraints variables are non-negative. Okay, so it can be negative. Okay. So this window pops up. Okay, and then we say okay. Now what I see is that what I'm getting is all three eigenvalues are the same. Okay, so that means whatever values we have given have converged to the nearest point. Okay, so how do we check whether this lambda 1 equal to lambda 2 lambda equal to lambda 3 is the only solution, or there are different solutions to it? Okay, so what we can do is just let us put let me do it here. So you put let's say that you assume the values to be like, instead of random, you take it like say 1 to 30 or so. In this case we have taken 1 to 30. Okay, here how do we calculate this? We'll say what? M determinant okay. So M determinant of S, okay, minus B, okay, into here we are taking this random value. So let me take this value here, whatever is, I'm assuming that, okay, and enter. So understood this? So, and then you can just drag it. Now these are your eigenvalues. If you take from a range from 1 to 30.
So they are the trial values, right?
Yeah, those were trial values. Now we are trying to see whether these trial values are actually, whether they're just 5 or there are non-equal also, right? You have separate 3 values or just 1 value, as it was converging to only 1 point here. So if you just look at this here, okay, so one value I can see here is for 26, lambda 26, this works out to be 0. Okay. Where else? Somewhere here, because this is going from negative to positive. Okay. And one is somewhere here again around 5, it's going positive. So if you say, okay, let's we're searching this, let us have an idea of how it looks like. So we can just say insert a scatter of xy.
Hello, sir.
Yeah. So
Hello,
yes.
sir.
Yeah.
So after doing that solve part, what did you exactly do? Can you repeat once again?
Yeah. I'll do that. Okay. Uh, Format this. Okay. Marker option built in. You can make it small. And then you can just see where are the values. You can see, so this is your graph. So around 5. This is around 20, 21. Between that and here around 26. Okay. So this seems to be that I have given values somewhere which are around this value, right? So I had given something 2, 4 and 5 or something, or 6 or 7. So all those values, it found a solution which was near those values. Okay, so they all converge to this value of 5. Okay, so let us do one thing. So we have a rough estimate of what the values are. So let's say 4. On the other one, let me call it as something 19 or so. And let me give a value of around 25, which I'm seeing from the graph. Okay. Now let us run this solution again and see. Okay. Somebody was asking what did I do? Okay. So let us do it again. So we'll go to data. Okay. Go to the solver. Okay, so what I can do is reset all. You need not reset it, because since I'm showing this or set objective, you set that value to some thing which has got nothing to do with this problem for the time being. What is the values you want to vary? You want to vary this values. Okay, and then you will add the constraints. What are the constraints? That this left hand side should be equal to the right hand side, right? So with these values, and these are the uh, determinant values which I am getting here, which has to be set to 0. So the reference cells are this, and this have to be set to zeros, right? So there are other constraints also. You can say greater than, less than, but here we are using equal to. Okay, so till here it's fine, and then you say okay. Okay, now I can say just solve it. It will solve it. You can add also. I mean, next time we can add a different situation here, and then you'll have to select and solve that part only. Okay, for the time being, I have only one subject to the constraint, so therefore I'll say solve. Okay, so this window pops up saying that keep the solver solutions. Okay, and now here you say you get, so we had some rough estimate from the graph here, and from that now you can see it converges to 5.189, and the second value is 20.8, and third value which we are getting is 26.
So can you show the formula of N and O?
Which formula?
N and O. What you have done in N and O? Column number N and
10 and
Yes,
oh,
sir.
ah,
Yes, sir. What you have done?
that, okay, this values I have just taken. See, I got only 5, so I wanted to check in a given range whether this function has some other eigenvalues where this condition of is satisfied. Okay, so what we are doing is you could have taken minus 10 also. You could have some solutions which have minus. So randomly I am taking some 1 to 30. You may say, how do I know that? Okay, I worked on it as, for example, if you don't want to do this, okay, let's say I put my minus 10, okay, minus 9. Let's drag this. Okay, so these are some values which we have. Okay, so this is a range I have chosen. Okay, I'll say equal to. Now, instead of just taking these 3 values which we had done here, the same formula I am entering here, but now with minus 10, then minus 9, minus 8, and so on. So this will be equal to what? What was the formula there? It was determinant of, in this case, S minus lambda I, right? So S, first of all, M determinant. Okay, so S that you see here, it is selected, minus B, which is our identity matrix, multiplied by the first value in this range, and then see. Okay, so let's just drag this. Now here you can see that it is just diverging off. Okay, so this is our area of interest, so I can narrow it down, right? Okay, it has not taken the whole range, not, it's taken only till 30. So you can see here, so this is of no area of interest for us. So it is just diverging of here, and then again you can see here that it goes down with some minima it seems, and then it is diverging up. So that's why what we did was we're not interested in this. Okay, and
There's some problem with the x-axis.
so let me just plot it. Okay, so this is what we have. So from looking here, so around 5, here around 20, and here around 25. So this is the values I can choose somewhere here, and somewhere here, so that they converge to give me a solution. So is this clear?
So in the determinant
Yes,
part,
sir.
Yeah.
so in the determinant part, where we put constraints, it should be 0 equal to 0. I mean, why aren't they giving us like the value 0 in all of the 3 equations? Like in some, it was giving 0.00003, which is actually a little error. Like, yeah, in the minus 0.003. I mean, it is going somewhere near to 0, but why isn't it picking a point which is 0?
This one.
Yeah.
Okay. So it means it is going up to which digit? The 4th digit, right? So it is performing iterations. It will not give exact, but if you want to just see 0, it is this. Okay. So I have kept it so it can display all the digits. So is this fine then? Okay, so it is going to go to 0. There is nothing as when you're doing a calculation. Okay, you can always approach a number 0. Okay, but doesn't mean that infinitely it will be 0. Unless it is an exact this thing, right? So it is calculating, taking this values for this matrix. This value has to go to 0. So it is adjusting these parameters such that we approach 0 for these values.
Can I add one comment?
Yeah, sure.
See, when you actually solve this analytically, this first number is something like root 61 minus 5 or something like that, right?
Yeah.
So this number, that first eigenvalue and second eigenvalue are actually irrational numbers. But irrational numbers have infinite decimal places, but our computer has a limitation. So it will have finite decimal place. And therefore, when you do calculation with that, it is not going to go to 0, because up to certain digit only it will give you the value, because you are not taking exactly that complete irrational number. You are truncating it to certain decimal place depending on the value. Whereas the third
Here
value
it
is
is
26.
exact.
It is
That
the
is 0.
integer. That's why you are getting 0.
Okay, sir, understood.
Okay. Fine. So now our next job is for this values of eigenvalues, we have to find omega x, omega y, omega z. Okay. Now when I use this value, this directions of omega x, omega y. So finally omega will be in the direction of your angular momentum. So if I use this eigenvalues, okay, and then solve this part of it, that is s minus lambda I, then now in this case the angular momentum is in the direction of your omega. Okay, so till now when we put these values, random values, it was not. Okay, now if we specifically take these values, so let us say for e is equal to 5. Okay, so that what is that we are going to do now? Can see here, we'll say s minus lambda I, right? So simple, s minus lambda I is this value which is calculated here, right? And b is your identity matrix. So s minus lambda I. Okay, so now this is an array. Okay, so that's why it will not allow you to do that. So you will say shift, control shift, enter. Okay, so how will you do that? Basically you select a 3 by 3 equal to, equal to, that is S minus B into, so that will give you this values. Now how about finding the eigen vectors? So we know this. Okay. Now remember this, your right hand side is 0. These are homogeneous equations, right? So we have calculated this, we have got this, we have this, right? The right hand side is 0. Okay. Now when you try to solve in Excel, it will give you 0 as an obvious solution to all of them. Okay. So these are what? 3 simultaneous equations, right? So this into this plus minus 6 omega y and omega z will be 0, right? So should we write those equations? Okay, so it will be like, say, 2.8. Okay.
Or you may just write that, na, that Ixx omega x, Ixy omega y. You don't want to solve that, right? So you may just mention that 2.810 is Ixx.
Yeah,
So in that format also.
yeah. So yeah, that is fine. Yeah. So this is Ixx, this is Ixy, Ixz, Iyx, Iyy, and Iyz. So this components multiplied with this omega right hand side. As I said, but if you try to solve it like the previous, the linear simultaneous equations which I did here. Okay. Now this is 0. Okay. So the problem is that this also works out to be 0 when you try to solve using Excel. So what we will do is use the Cramer rule. Okay, so you have 3 equations here. So the first element, let's say if you want to calculate your omega x, okay, then your omega x is Ixx omega x, right? So you leave this whole column, okay, and this row. So the remaining 4 elements. Now this will, when you're using Cramer's rule, you know that this will all omega x, omega y, omega z will give you not exact values, they're ratios. Okay. So it will be like omega x. Anyway, I'll say write w. Okay, wx by, okay, so it will be divided by the determinant, okay, of this 4 elements. Determinant of this, you leave this whole column, this whole row, so this, okay, so determinant of this elements, then you will have equal to, this will be equal to omega y. Okay, so determinant when you're taking omega y, okay, so this element, okay, so you will leave this. Now here for doing determinant, it will not allow you in Excel, so you'll have to actually multiply this term and this term, okay, and then will be equal to w or omega z. Okay, so leave this column and this row and the determinant of this 4 elements. Okay, so let me just calculate that. So this will be equal to what? It will be determinant of this element. Okay. Now when I am doing this equal to, okay, for the next element, okay, so this is not allowed. Okay, so I am taking these two equations, right? The second and third one. So it will be -6, that is this cell, into this minus so yeah, when you're using the Cramer's rule, there's the second element is minus omega x. Okay, omega x is positive minus omega y and plus omega z. So that is 124, and then this will be equal to determinant of, this is not allowed, so this elements. Okay, you can normalize them by dividing them by root of square of this plus square of this plus square of this, which I have shown here. You can do that. Okay. The other important thing which we need to calculate is what is the angle. Okay, so if we take the first two elements, okay, say,
Sir,
yeah,
sir, in the second, the first, sir, can you show the second element's formula again?
yeah, this one. Okay,
Sir,
so when you
omega
see
y.
this is the first equation, second and third, right? So we
Yes,
are
sir.
using the second and third equation. So when I'm using this for I-axis part of it, which is omega x, okay. So what I will take is
So
this
then first
four
element,
elements.
first row and first column would be neglected, and
Yeah,
the
there's
rest.
just four elements,
Yes,
right?
sir.
Uh,
And the second one?
when you're doing the second one, okay. So you will take, now I cannot use m determinant because these cells are not continuous. So you will say -6 multiplied by 20.81 minus 0 into 0.
Okay.
You will use the same equation. As you know, when you're using right ijk, how you do that? You use you don't use these elements, right? You use the elements under I and k. So similarly, and when you're using this one, okay, so it will be the determinant of this. Okay, so one thing we can see here is that omega z is 0.
Yes, sir.
Okay, so omega x is this much, omega y is this. Okay, so we can also calculate what is the angle between them. Okay, we'll say equal to degrees. Okay, yeah, we want the tan inverse. Okay, so you say a tan. So tan inverse formula is a tan, and that is this divided by omega y divided by omega x. Okay, so the angle works out to be around 25 degrees with respect to the x-axis.
So,
Yeah.
How do I did you created that matrix for E5? I'm getting an error.
Which one?
Oh, you have created this matrix for E5 now. I minus lambda I matrix.
I minus this one.
Yeah, this one.
Okay. What is the problem you're getting? So you choose the three cells
Yes.
equal to whatever is the matrix. In our case, it is S. S minus my identity matrix is B. Okay, multiplied by this value. Control Shift Enter.
Yeah, I got it.
Yeah. So this is how you can get the angle. Now, what is the other value of lambda we have? So the eigenvectors will calculate for 20.8. Okay, so same thing. So instead of multiplying it with the first eigenvalue, you multiply it with the second one. Okay, so you will get this. Okay, again use the Cramer rule. Okay, and calculate the angle. Now this angle works out to be minus 64.9. That is almost 65. So how much is the difference? I'm audible, right?
Yeah, 90.
90. So they are perpendicular to each other. Okay. So we said that we can, if the moments of inertia, along the moments of inertia, okay, it would be symmetric around the orthogonal axis. So for this value and this value, so the axes are at 90 degrees. So there's a symmetry around. Now for the third one, we calculate. Okay, here omega x is 0, omega y is 0, and we have only omega z. So that was our, where was that problem? So if you take this one, so along the perpendicular axis omega z, this whole thing is symmetric. Okay, so there's no omega x, omega y. Okay, so it is rotating in the xy plane. Okay, with omega perpendicular to the plane. Okay, so it is rotating in the xy plane. Okay, so that's why there is no x and y component of it along x and y, and we have only omega z. There is, and so this is one. The other axis is this, which is at 25, and we have another axis which is perpendicular to this at minus 60. It's fine. Any questions? I'm connected, no?
Yes, yes, you are connected.
Yeah, sometimes. Okay, can I go to another problem so that some practice?
When you say 25 or minus 65, what is your reference line? Is it the diagonal?
25 with respect to the x-axis.
Diagonal. Diagonal. No, the x. 25 with respect to the x-axis. But you're finding out omega x.
Yeah, so omega x is in that direction.
Okay. All right, thank you.
So, sir, here the eigenvectors which we have got, they are the principal moment of inertia.
The eigen
Vectors
uh,
are the principal moment of inertia.
no. The angular momentum is in the direction of the omega. Now, the moment of inertia, by saying that the determinant, okay, of your moment of inertia tensor minus lambda I, you have diagonalized it. Fine, and you have found these values. Okay, so now this has become a scalar. You're getting some values. Okay, so that whole problem has been simplified to these three values, which you will use to find the angular momentum directions. Sorry, angular velocity directions. And you have the angular velocity, angular momentum also in the direction of this. So we didn't knew what were the principal axes, so we did this whole process to find the principal axis. Where the moment of inertia vanishes. Asymmetric, you can say, about that axis. Is this fine, or Mahesh? Can go to the next one.
Yes, yes.
Okay, this one here problem again, a dumbbell problem. This dumbbell is lying in the XY plane. Okay, so the coordinates we can take it as -1, 1, 0. So the z-axis is 0 here. So 1, -1, 0. So, and we can take the mass as 1. So on the same lines, we construct, let's say m1, m2. Okay, since there are only two masses, the coordinates are -1, 1, 0, 1, 1. Sorry, there's mass 1, 1, -1 and 0. Okay, so what you're going to do is calculate the moment of inertia tensor. Okay, so we know how to do that. So you will say that is m1 y square plus z square. Okay, and then m2 y square plus z square. Okay. So once you have calculated this, we can choose some random values, or you can initially plot a graph for it and see where you can get this values. Okay, so let us start, say, from -1, 0. Here again we'll write, so it is M determinant here. Your vector is, I think, I. Yeah. I minus B. Let me take -1. Just drag. Take an XY plot. Okay, so here, like from -1, it seems to be all of them on the line only. So we are interested only up to maybe up to 6. Okay, so 0 somewhere between 4. Okay, so 0 and 4, that seems to be the values. Okay, so you can give some 1 here, 3 here, maybe 6 here. Go to data, solver, set all. The constraint variables are going to be this. And constraints equal to, and so we get this values. So again we'll come back here. Now for E is equal to 0 and E is equal to 4, we'll find the Eigen Vectors, omega x, omega y, omega z. Here we written 1, 2, 3, but omega x, omega y, and omega z. So I get 8 minus 8, 0. Okay. And then we can calculate the angle between this. You can see it is, so you will say degrees tan inverse of that. So that is going to be 45 degrees. Means the axis is along the line joining the two masses. That is 1. Okay, there's another interesting thing. If you look in this moment of inertia tensor, this value is 2, 2 and 4. So Ixx is 2, Iyy is 2, and Izz is 4. So if you remember your perpendicular axis theorem, okay, so your Iz was equal to nothing but your Ix plus Iy. Okay, so since this is in the xy plane, so this Iz will be Ix plus Iy. So this tensor which you have calculated is right. So this perpendicular axis theorem, you can see here, is working. Okay, so there's no omega z component. It is in the xy plane, and therefore the angle is minus 45 degrees. Okay. Yeah, now if I take E is equal to 4, okay, then I get omega x, omega y, and omega z also equal to 0. So this doesn't make any much sense. So it's a trivial. अतुल सर कुछ और है, एक आपका भी प्रॉब्लम है? Okay, so there's one more problem here. Imagine a cube, let's say, right? So the coordinates of that are 1, 1, 0. Okay, so and this is 1, 0, 1. Okay, and the other is 0, 1, 1. So this is in the xy plane. Okay, this is in the xz plane, and this is in the yz plane. Should I? अतुल सर का प्रॉब्लम है. Just see. Have the diagram. Yeah, this one. Okay, so 1, 1, 0. Okay, so this is in the xy plane. So 1, 0, 1. So this is in the xz plane, and then 0, 1, 1. So in the yz plane. Okay. So we can calculate this values using the same formula, but here we'll have m1, m2, m3. Substitute the coordinates. Okay, and then calculate the eigen values. Okay, now the eigenvalues which we get here is 2 and 5. Okay, for the eigenvector 2, we calculate the eigenvalues which work out to be 3, 3, 3, which is 1, 1, 1. So the angle between omega x, omega y 45 degrees, the same thing with you take at omega z. So this is basically at 45 degrees. Okay, and okay, something interesting here happens is that for lambda is equal to 5. Now this works out to be just -1, -1, -1. So basically you have 3 unknowns and you will have only one equation. Okay, so you will not be able to use the Cramer rules because you can have infinite number of solutions for this. Okay, so but if you choose, let's say, one of them to be 1, Okay, and it is omega x plus omega y plus omega z is 0. That is what you will get from here. Okay, omega x plus omega y plus omega z is 0. So if I choose omega x as 1, okay, as I have done here, okay, I can choose omega y as minus 1, then omega z will be 0. If I choose omega y also to be 1, then omega z will work out to be minus 2. Okay, so for if this are the directions of omega, which will be the angular momentum directions also, and then the angle will be minus 45 degrees in this case. Okay. Any questions? Any part of it? So you can try out different building metrics, moment of inertia tensors for different situations, and then calculate out the eigenvectors.
Maybe 1 or 2 assignments can be given to them, and design
Yeah.
some assignment, and we can upload that.
Sure.
If there are nothing on the chat, I'll stop recording.
Fine.